Okay, when I hand a test back, what I typically do is I'll talk a little bit about the test, not a lot. I'll talk about ones that were commonly missed. I don't want to spend a lot of class time on the test, but there's a few things to discuss. But I will have the keys scanned and posted on D2L. And it'll be in that module that says exam prep materials or something like that. There's two versions to the test, a version A and a version B. I don't know if you noticed that or not, but so look at the front of your test, you'll see which version, and then you know which key to go get. All right? And then once you see the key, if you still have questions about how to work a problem or why that's the right answer, make sure you email me. Have I mentioned that the test or the final is comprehensive? Yeah. So this stuff's going to come back to bite you again if you don't learn what you didn't know. Understand? All right. So make sure you do that. Just looking down through it, I don't see anything on the first page that was real commonly missed. Probably the most commonly missed thing on the first page was it's the problem about the political poll conducted, and you're supposed to circle any of the statements that discuss design of the survey. That one was fairly commonly missed. What is it? What do we mean when we say the design of the survey? How it was done. So anything that talks about how the research was conducted, that's design. Right? So which of those statements talks about how it was done? The one that says they interviewed 1,000 randomly chosen registered voters. Right? They interviewed. That was one thing they did. 1,000. Their sample size. That's part of the design. How they selected them? Randomly. That's in that statement. Right? So all those things are about the design. Nothing else. So there are people that circled that, but then they circled a whole bunch of other stuff too. So you missed partial credit for that. 3 points. Oh no, I'm sorry. 6 points total. There's 3 parts to it. Then on the second page, this one was fairly commonly missed, I guess. The one that had the histogram, and then it had the frequency table down below it, and then a whole bunch of questions about that frequency table. The class width was 10, and that's the distance between the starting point of any two of the classes. Not like the first class is 40 to 49, so a lot of people put the width as 9. It's 40 to 49, but it's actually 40 to 50 is the next class. Right? So each class, it's 10 units to get from class to class to class. So the class width is 10. Midpoints, how do you find the midpoint of a class? The average of the upper and lower bound of the class. So the midpoints, it depends on which version you're on as to which one they ask for, but it's either the first or the last. And then the one that was commonly missed was part E, and it says use the frequency table to compute the approximate sample mean and sample standard deviation. So X bar, I'm looking at version A. If you're on version B, it'll be a slightly different answer. But that is approximately equal to 72.9. Now, how do you get that?
You find the midpoint of all of your...
Okay, so midpoints go into what? L1. Into L1. And then the frequencies go into L2. And then you do 1 var stats L1, comma, L2. Or if you're on the newer form, it would say list L1 and then freq list L2. So there were people that indicated that they did this. They put the midpoints in L1, the frequencies in L2, and then they did 1 var stats, and they even wrote out what they did. Then I did 1 var stats, and I hit enter. What happens if you just do that? It does L1, it ignores L2, and the answer that you would have got, 84.5, which is the middle of those midpoints. Right? And then there were people that, there was a fairly common mistake 40.9 or 40.6 or 40 point something for the mean, right? And it took me a while to figure out what was, how that number was coming up so often as an incorrect answer, but I finally figured it out. What was happening was they were putting the frequencies into L1, the cumulative frequencies into L2, and then doing L1 comma L2. But those frequencies don't have anything to do with the pulse values. It's just how many people had that pulse. So you don't want a mean of the frequencies. You want a mean of the pulses weighted by the frequencies. So then I got a little bit smart alecky. Really, I wasn't trying to be smart alecky, but I got to thinking, that's going to seem like I'm being mean a little bit. But I was doing this. If you had that as an answer, I was circling it and drawing an arrow up to the histogram, which the histogram, the two bars that are same height, you have 70 right in there, right? Where is 40.6 on that histogram? Look at the histogram. It's right here, right? There's 40. So I was drawing an arrow up and saying, that's your mean? Trying to get you to do what? To look at your answer, see if it makes sense. Does it seem right that the mean heart rate would be 40? Not looking at the data, the average should be in the middle. So it ought to be somewhere around 70. So I always encourage people, when you work these kind of problems, to get a ballpark estimate in your head of what you think the answer ought to be close to, then go work the problem. If you get an answer close to that, then yeah, I probably got it right. So I would look at that and go, well, it ought to be around 70. Then I go work it, I get 72.9. Yeah, I probably got it right. But if I get 40, then ooh, something's not right. So you start looking for your error. If you don't pay attention to the numbers, then well, I forgot what I was talking about. There's your test. Numbers look just fine when they're sitting on your calculator, but when you put them in the context of the problem, you realize, well, that number doesn't make sense. So now that we're into probabilities, the same thing is going to happen all the time. People are going to give me an answer to a probability question like, probability is equal to 2.38. Wait a minute. Does that make sense? Probabilities must be between what and what?
0 and 1.
0 and 1. You cannot have a probability bigger than... Now, what's going to happen on your calculator, I haven't done that. I'm not sure we've hit one like this yet, but your calculator, if it gets really, really small, close to 0, it'll default out of listing all the decimal places to go into scientific notation. So you might see 2.38 and then, and some other numbers, and then a little e minus 9. What does this mean?
Times 10 to the negative 9.
Scientific notation, which means exponent of negative 9. So this is 2.38 times 10 to the minus 9th power. And people don't notice that sitting out there, and they write 2.38 as the answer. Right? So if you write an answer down that's bigger than 1, go back and go, ooh, I bet I missed an e minus something out there. Okay? Okay, on the next page, there wasn't anything real commonly missed on the third page. There were some people that didn't read the stem and leaf plot right. There is a key under it, but there was several people that, let's look for instance at the one that's stem of 5 and then it has a 0, 3, 3. There were people that entered into their calculator 5.033 as a single number. That's a fairly common mistake. What should it be?
5.3.
5.0, 5.3, and 5.3. There's 3 numbers there represented. Okay. So I got used to looking at the incorrect answers and realizing, oh, then that's the mistake they made. Right? But it takes a while to figure those things out. But. Okay, last page was pretty good. I was pleased with how well the last page did. Unfortunately, there was a fair number of people who got every number on that page right. They got the regression equation right, but they still missed quite a few points on this page because of all the interpretation questions. That's where the points were missed. So I keep saying that in here, but in an intro stat class, in my opinion, it's more important that you know what the numbers mean than you know how to compute the numbers. Because software is going to do all this stuff for you. When you're out on the job, right, you're going to be using Microsoft Excel or whatever if you have to compute anything. But what's important is that number correct? And what is that number telling me? Right? So on part B, the second part of part B says calculate the coefficient of determination. What is that? That's R squared. And for this problem, depends on your version, but the one I'm holding, it was 0.916. That's version A. On the other version, it's 0.907. What's the interpretation of that number? What's the interpretation of R squared? Go ahead.
But there's a 0.907 swing variability in y values in relation to the x values, or for x there's 90.7% correctness.
Okay, so R squared tells you the percent of variability in the y variable. In this case, that's grades. So 90.7% of the variability in grades can be explained by how many hours they are unsupervised. That's the interpretation of it. Okay. Then there's an interpretation of slope. There's an interpretation of intercept. I remember making the joke a few times that on the test, if I say, give the interpretation of the number B0, and you say it's the y-intercept, I'll say that's true, -3. Right? Because it's interpretation. It's true, it's the y-intercept, but I don't know what that means. Always explain things like you're explaining them to your mother. If you just tell her, oh, that's the y-intercept. Well, your mom might be smarter than mine, but don't tell her I said that. But what I want to know is, intercept that's the expected grade that somebody would get if they have 0 hours unsupervised. So they're supervised all the time. They should get an 84.5% grade. Okay? That's what that means. Okay, so any other questions about the exam? Yeah.
Okay, so if you have like -5, how do you divide that to get like the percentage?
It's 100 minus whatever you got. So if you have a 5, you got a 95. There's 100 points possible. Right? Everybody good on that? Okay. Let's get to probability then. We're going to finish up what we're going to do with probability today. We're going to work some problems, but I also have a few kind of what I call interesting counterintuitive probability problems to talk about, just to give you an illustration of how things sometimes aren't what they seem. And you have to think about probability problems and see if it makes sense, but unfortunately sometimes what makes sense isn't right. So it's troublesome. But we have one more thing to finish up in section 4.3 before I get to the fun stuff. So let's do that first. Let's see. Yeah, here. And this is called the fundamental counting principle. And there's nothing too difficult here. And you can use this principle to help compute probabilities. But a lot of times you can compute the probability even if you don't remember this principle just by using the multiplication rule. I'll show an example here in a second. So the fundamental counting principle, this is a complicated paragraph. Sounds horrible, but it's not so bad. Multi-stage experiment. So that means you do one thing, then you do another thing, then you do another thing. Now, it might all sort of be happening at the same time, but at least if you can break it up and say, well, you got k things like this and k things like this and so on, right? So then if the first stage has k1, so the kinds for the first stage, the number of kinds for the second stage, third stage, and so on, then the total number of possible outcomes is just the product of those. Okay? Did we talk about the pizza problem? How many pizzas can you make? Yeah, we did. See, I knew we did. Right? So let's say we have 4 kinds of vegetables. V for vegetable. And we have 5 kinds of meat. Are there 5 pizza meats? Yeah? Okay. At the good restaurants, right?
2 types of thickness.
Okay, good. So 2 types of crust. Right? And then sauce. So you can have a spicy sauce or a non-spicy. How about that? So 2 sauces and 3 cheeses. If you choose one of each of those things to make your pizza, how many kinds of pizza can you make? What does the counting principle say? If there's K1 kinds of vegetables, K2 kinds of meats, and so on, then the total number of ways is the product of all those things. So think about, I got 5 different things to choose. How many ways can I choose the first one? That's my vegetables. Oops. I got 2 that start with C, so I have to use them. So vegetables, there's 4 of those, 5 meats, 2 crusts, 2 sauces, and 3 cheeses. Multiply them together. What is it? 240. So there's 240 kinds of pizzas you can make. Combinations of pizzas. Right? Now it gets more complicated. We won't get to problems like this because I'm going to skip the last 2 sections of chapter 4. But if you say, well, you're going to choose 3 vegetables and 2 meats, so you have more than one of each, then it's like, well, how many ways can I choose 2 meats out of 5 possibilities, and so on. Right? That's section 4.4, and we're gonna not do that. But right, so that's the fundamental counting principle. So let's look at some problems from the book on this. Let's see. I think if I go this way. Back 1 page, I guess. There it is. Fundamental counting principle. Let's start with number 23. Henry is setting a 6-character password on his computer. He is told the first 2 characters must be letters and the last 4 must be numbers. No character may be used twice. How many choices are there? Now, I always have to do this with blanks. It's the way my brain works. But you organize however works for you. But I'm going to make a password. It's going to have 6 characters. So I'm going to make 6 blanks. Right? Now, the first 2 characters must be letters. The last 4 must be numbers. And there can be no repeats. So you start filling in how many ways can each blank be filled. So how many choices do I have for the first blank? 26. How many choices for the second blank? 25, because I've already used 1 letter. And then the next 4 have to be numbers. So the first number, how many choices do I have? 10. Yeah, 0 through 9. Zeros are digits. So 0 through 9 is 10 numbers. Next blank, 9, 8, and 7. Multiply it all out. 3,200,000 and what?
76,000.
Even?
Yep.
That seems like a lot, doesn't it? So if somebody sat down at his computer and tried to hack into it on 1 attempt, that's the probability that they would... Of course, they'd have to also know the pattern, that it's 2 letters, 4 numbers. Because otherwise, they would have even less probability because they might mix letters and numbers all over the place, right? But in terms of, anybody here in computer science? Nobody's a computer science major? Well, what do you think about a password like this? Is that a strong password? No, by today, that's a pretty weak password, right? So nowadays they want 20 digits with capital and lowercase being different, and any combination of letters and numbers and special characters. So this number is already at 3 million. You make a 20 digits and make all those other possibilities, and it goes up into the trillions, right? So they supposedly are unbreakable. All right. How about 25? How many even 4-digit PIN numbers can be created from the digits 0 to 9? Write your 4 blanks down and figure it out.
What does it mean, even 4 digits?
Even 4 digits. So what does that mean, even? It ends in an even number. It can start with an odd number, like the number 5,122 is an even number, even though it has a 5 in there and a 1 in there, right? So it's only the last one that has to be even. So you got 4 blanks. Fill them in, multiply it out, tell me what you get.
What are they cutting 0 out of? Neither?
Yeah, zeros.
I think 0 is considered an even number.
Okay.
Are we assuming that we can repeat numbers?
He just asking a very important question. Can we repeat numbers? Does it say you can't? Then you can. That's the assumption you make. And if on a test, sometimes I forget to explain everything completely. And so if you find yourself having to make an assumption, then write out, I'm assuming here that repeats are okay. Then I'll give you full credit, even if, well, that's not what I meant, but, right? Understand? So what do you get? 5,000. It should be 10, 10, 10, and 5. Multiply it out, you get 5,000. Okay, work number 24 on your own. I'll read it for the camera mostly. There are 6 children, 3 girls and 3 boys, singing in the school program. As they line up to perform, the choral director insists that the first person be a girl and the last be a boy. How many ways can the children line up? So you got a line of 6 kids. First one's got to be a girl. Last one's got to be a boy. The other ones don't matter. Got a number? Okay, it's not quite right.
I didn't do it right.
No, not quite right either, but it's not quite right either. Because once you pick that person,
Then it takes
they're gone, right?
Mm-hmm.
And then once you pick this person,
They're gone.
right. So yeah, and you're doing the same thing. The mistake that so far everybody has made is once you fill in one of these middle blanks, that person now is out of the pool. So the number of choices for the next one goes down by 1. Right?
361.
I don't remember the answer off the top of my head, but what'd you get?
I just did 216 right now. It's right.
That is right. I don't know the answer, but I know the pattern. And that is right.
Or is it contours?
That is correct.
That one's correct.
Yeah.
Well, wait a minute.
3 girls, 3 boys.
That's not quite correct. You don't know how to do it? Okay. Yes, that is not correct. And look around here at hers. You picked a girl. You have 3 ways to do that. That's right. Okay. And then you pick a boy, and then you got 4 of these. Well, how many people are left?
5.
Because this girl's this girl can't stand over here because she's standing there.
Yeah.
And this boy can't. So there's only 4 left. Now, you picked one there. Yep. So you picked one. Once you set somebody in a blank, the number of people to fill the next blank is down by 1. Right? So 3 ways to pick the girl to go here. Everybody got that? 3 ways to pick the boy to go there. The common mistake I'm seeing now is I'm seeing 6, 6, 6, 6, which isn't right because 2 kids are gone. So there's only 4 left. So then I was seeing 4, 4, 4, 4. But, okay, I agree, 4 right there. But now that person's standing there. You can't also have them stand over here. So the number of choices here is 3, 2, 1. So what is it, 216? Okay. Okay, that's probably enough of those. Let's go to do some probability now out of this. Oops, apparently not that direction. Oh, here we go. This thing always confuses me, but let's do this number 30, right? By the way, these that are in the book, I know you've all been doing all of the odd ones every time in the book, right? Because the answers are in the back. So if you need practice, go try these odd ones. The answer's in the back, you can see if you got it right. The answer to the even ones aren't in the back. But if all you're doing is trying to certify on first shot, you get lucky, you're cheating yourself, right? So don't do that. Let's do number 30. It says a couple having twins is deciding on names. They narrowed their choices to 5 boy names and 7 girl names. Now they're having twins, right? So the new father's parents, that's going to make the wife mad. The new father's parents like only 1 of the boy names and 2 of the girl names. Assuming that the new parents have 1 child of each gender, so they have a boy and a girl, what is the probability that the names they choose will make the new grandparents happy? Why does it matter whether they're happy? That's what my wife would say. I don't give a dang if they're happy. Can you work it? Got a question or an answer? Okay, and tell me what you... Okay, good. That is right. And you did it without using... Well, you sort of used the fundamental counting principle, but I picked this problem, or this set of problems, because they're all similar, to illustrate that the counting principle is only one of the ways that you could work this problem, right? But what's the total number of ways that they can pick the 2 names? You've got 2 kids to name, a boy and a girl. So let's say that's the boy and that's the girl. How many ways? There's 5 boy names and 7 girl names. So there are 35 total combinations that they might choose. The parents like 1 boy name and 2 girl names. So they have 2 ways that they're going to be happy. So 2 out of 35 is the answer. Right? What? What did you say?
She just added.
Added them or multiplied them?
Added. I just put 3 over 12.
Oh, but you're not saying you had the right. I thought you.
No, I didn't have
I thought you were saying I just added them and I got the same answer.
Yeah.
But I thought you can use the multiplication rule and get this right also. Now what's the multiplication rule? We did it last time, but it's in this section. In general, the multiplication rule is the probability of A and B is equal to what? The book uses E and F, same thing. Probability of A times don't just say probability of B. That works if they're independent. But if they're not independent, then you have to condition on A occurring. Right? Now what about here? Are they going to be independent? The choice of boy name, does that influence the choice of the girl name? Probably not. So they're probably independent events. So we don't have to worry about it. But the probability that they're happy, this is how my brain works. I start with a word or a phrase or something that's what they're asking. What's the probability the parents are happy? So probability happy. Then I try to put it into symbols. How are they happy? They're happy if, right, the boy name is good and the girl name is good. Okay, how does that happen? Well, this is an and, so I can break it up. We've decided they're independent, so I don't have to worry about conditioning. What's the probability that the boy name is good? 1 in 5. Now, what's the probability that the girl name is good? 2 of 7. Multiply them together. 2 out of 35. So without really knowing it, you're using the fundamental principle of counting, but it happens through the multiplication rule and the denominators. But it's exactly what we did. We took 5 times 7, that became the bottom. We took 1 times 2, and that became the top. Right? So the multiplication rule has that built into it. Keep in mind that the multiplication rule and the addition rule can extend past 2 events happening. So if I deal a hand of poker, I'm dealing out 5 cards. You can find the probability of a particular hand by saying, well, what's the probability of the first card being this, second card being this? And you got 5 things to multiply together. But you just do that. You just string them out. Okay? I don't know that I have a problem in mind from the book, but here's a common problem that I like to put on tests. Let's say you have a club of boys and girls, right? And you have to pick 3 officers. And in that club, there are 20 members, and 15 members are boys, and 5 members are girls. Okay? Everybody keeping up? Now, you're going to put all 20 names in a hat, and you're going to pull out 3 of them to be the officers. Okay? You're going to randomly choose 3 to be the officers. What's the probability that all 3 are girls? Compute that probability. And you can do it with the fundamental principle of counting, or you can do it with the multiplication rule. It's okay to work together on these things when we're just doing them in class. I don't think that's quite right, Stephen.
No.
You got an answer? Okay, and you did it with all 3 are girls. That's not quite right. No, I think that is right. That should be right. Okay, what was your answer? 1 out of 1 over 114. Is anybody else getting that same answer? You raising your hand? That's what you got? Okay, and how'd you get it?
1 because that's
20, which is 4.
Okay.
And then 4 out of 19 is
5 out of 20 times
4 out of 19.
4 out of 19. And why is it 4 out of 19? Because one of the girls has already been selected, right? And then next one, 3 out of 18. Is that what you got? Okay. And then the top is 20 times 3 is 60, and the bottom is, I can't do that one in my head. 6,800, like that. And then you reduced it, and it was 840. And then when you reduced it, you got 1 out of 114, you said? Okay, what is that as a decimal? 8.772 times 10 to the negative third. Everybody do that on a calculator and see the E minus I was talking about?
Not all.
Yeah, it kind of depends on the settings of your calculator. You may have enough space to have it string it out, but...
So would you prefer an answer like that or like 0.0087?
I don't care. This is dandy. You can do that. So, for me on a test, I don't care if you write it as a fraction that's not simplified, a fraction that is simplified, or a decimal. Any of those things are fine. On the online homework, they will say enter either as a decimal or as a simplified fraction. So they would not take this answer. And that's just so they do less error checking, right? But they would take this one. So, but okay, now I skipped a step here because this is the way you guys were doing it, but all 3 girls, how is that an and statement? Okay, it has to be a girl and a girl and a girl, and I'm going to say girl on the first draw, girl on the second draw, girl on the third draw. Now we use the multiplication rule because it's an and that's probability of girl on the first draw times the probability of girl on the second draw, but I can't just do that. Why not? Because they're related. They're not independent events. Since they're dependent, we have to condition on what happened on the first draw. Girl on the first draw. And then probability of girl on the third draw given girl 1 and girl 2. And that's why these numbers keep stepping down. Both the tops and the bottoms of the fractions. They keep stepping down by 1 because you keep drawing another girl out. Right? So what about that number? Is that small number or big number?
Like 0.8%.
Okay. Yeah, it's less than 1%, right? 1 out of 114. It's less than 1 in 100 chance that that would actually happen. Right? And that's big. I mean, again, ballpark idea in your head before you ever work the problem. And I meant to do this and I forgot, but we'll go back. Pretend that I just now wrote this down. Get a ballpark estimate in your head. There's only 5 girls out of 20. So what's the chance that all 3 randomly chosen are going to be girls? That means I got to get 3 out of those 5 girls and none of the boys. That's probably not very likely because there's 15 boys. Right? So when you get a small answer, you think, oh yeah, that's what I expected. I expect a small number. If I ask probability of all 3 are boys, that's going to be a fairly big probability. Okay. All right. Well, I'm going to jump now. We're going to do a couple of whatever I have time for of some kind of interesting, fun probability things. And I know you're thinking probability is never fun, but trust me, it is. The first one has to deal with the Powerball lottery. You guys ever play the Powerball lottery? Good. Okay, so let me go to the next slide. This slide is actually outdated. This is several years old, and they fairly recently, the last 3 or 4 years, added more balls into the bin. So the probability, the way this probability is computed is in the remaining 2 sections of the chapter, which we're not going to do. So I'm just going to breeze over that. But you pick 5 balls from the white numbers, the white balls, and then you pick 1 red Powerball. Right? That's the way the Powerball lottery works. Right? Then, if you compute the probability of winning with 1 play, it's 1 in 146,107,962. That's the probability of winning the Powerball lottery. Well, now it's actually lower probability because they added some more white balls. And it's 175 million. But what we're going to do is, it still applies. Right? So, the point I want to make with this is sometimes our minds have trouble conceptualizing numbers that are either really big or really small. If I talk about 100 things, we can visualize that. If I talk about 1,000, okay. Once you get to 1,000,000, it's hard for our brain to process that, right? So, how likely do you think it is to win the Powerball lottery? Not very good. But how good is not very good, right? So here's an illustration. Sometimes it works if you can put it into some kind of a framework that helps your brain process the size of the number, then it becomes more obvious. Let's pretend that the jackpot on this particular play is exactly equal to your chance in winning. So the jackpot is 146 million. It'll get way higher than that, right? When nobody wins for a while. And they decide they're going to pay you in $1 bills. Right? So you got 146 million $1 bills. Okay? Now, to get an idea of how many dollar bills that is, let's take the dollar bills and lay them on the ground end to end so they're touching. Got it? And we're going to make a path. So here we go. We'll start here at Washburn. We'll go down McVicker out to I-70 and start heading west. How far do you think we can get?
Back to Washburn.
Do you think we can get to Manhattan, Kansas?
Yeah.
How about Denver?
Yeah.
Yeah, you can actually get to Denver. What about L.A.?
Yeah. I'm going to guess yes.
You're going to guess yes. Yes, you can get to Denver. Right? So I Google mapped it. You can get to L.A. But guess what? The semi-truck full of dollar bills that's following you as you're laying them down, it's still got dollar bills in it. So we go to Seattle. But we still got dollar bills.
Like how many
So we go to Maine. Then we get tired of turning the page, and here's the route. You go to Maine, you go to Miami, you go to Brownsville, Texas, you go out here to San Diego, then you backtrack, go to Atlanta, up to Chicago, over to Omaha, and back down to Washburn.
Oh my God.
That's how many dollar bills that is. Now, here is your chance of winning the Powerball lottery. Start walking. Follow that path. And at whatever point in your journey you start feeling especially lucky, bend over and pick up a dollar bill. If it's the one that I put a red dot on the back of, then you just won the Powerball lottery. That's probability. 1 in 146 million dollar bills. That's how far those dollar bills would stretch. Each one's about 6 inches long. Right? A mile is 5,280 feet. So it takes about 10,400 to make a mile. Well, 146 million is a whole lot of 10,000s. That's about a 14,000 mile stretch that those things would go.
Probability anybody wants
Okay, let me do one more. I'm not going to have time to do both of these, but this is called the Monty Hall problem. And there was a game show when I was a kid. There was a game show on TV back in the mid-'70s called Let's Make a Deal.
It's still on.
It's back on? It's probably not Monty Hall, because that dude's got to be dead. But oh, sorry, Monty, that was. But what Monty did was he showed you 3 doors, and he said, behind one of these 3 doors is a car. Behind the other 2 is a goat. Pick a door, right? So you pick a door. Say you pick 3. And he goes, oh, well, you picked 3. Let me show you what's behind door number 1. And he opens the door and there's a goat. Right? So Monty is always going to show you one of the doors you didn't pick, and he's always going to show the one with the goat. Right? Got it? So he knows where the car is. He's not going to show you your door, and he's not going to show you the car if you didn't pick it. He's going to show you a goat. Now, what should you do? He's going to say, do you want to stick with your original guess, or do you want to switch?
Stick.
Switch. Saw this in 21. You switch.
What'd you say?
Saw this in 21. You switch.
You saw it in the movie 21. That's right. They talked about this in the movie 21. You should switch. Your strategy should be to switch. Because if you switch, your probability of winning is 2/3. If you don't switch, your probability of winning is 1/3. That's counterintuitive. It doesn't seem to make sense. When this first hit the newspapers, there were mathematicians writing in and saying, I am appalled at the state of mathematics in this country because your answer is wrong. It isn't 2/3. But the probability of win if you switch. The probability of win if you do not switch. This is 2/3. This is 1/3. But wait a minute. If he shows me, if I pick door number 3 and he shows me door number 1 is a goat, how does the probability of me winning change if I switch to the other one? Well, think about complementary events. What if I don't switch? What's my probability of having picked the car right on the first try? 33%, 1 in 3, right? You have a 1/3 chance. So when do you lose if you switch? So he shows you a goat and he says, do you want to switch? If you picked the car correct the first time and you don't switch, you win. Right? But you only had a probability of 1 in 3 of making that choice. But he's always going to show you a goat, which means there's either another goat, because you picked right, or the car's in that other one. Right? If you switch, then the 2 out of the 3 times that when you don't pick the right one first, right? You pick right 1 out of 3 times. The other 2/3, if you switch, you win. Because he showed you the goat, right? So now you switch to the one where the car is. So 2/3 of the time, if you switch, you win. But only 1/3 of the time, if you don't switch, will you win. Because if you don't switch and you win, that means you had to pick it on the first 3 tries. You're taking advantage of additional information. He's giving you additional information, saying, well, here's one that we know is a goat. Right? Yeah, everybody's kind of frowning. That's counterintuitive. It doesn't seem like, why would it change? But simulate it. You can simulate it with cards. Deal out 3 cards, make one of them an ace. There's your car, make the other 2 goats. Right? Play, and you'll realize that if you always switch, you'll win 2/3 of the time. If you never switch, you'll win 1/3 of the time. Right? So if you're going to gamble, play the odds. Use the strategy that wins most of the time. All right, we will see you Monday. Have a great weekend.